a Portland Community College mathematics telecourse, a course in arithmetic review produced at Portland Community College. The key idea for this lesson will be the phrase two-factor used as a verb. In this sense, it means to write whatever you're being given as a multiplication problem. An example, if one were to say factor 12, one is being asked to write 12 as a multiplication problem. And of course, there are several ways of doing that, including 1 times 12, which we will not worry about. There is one more hidden way that you perhaps didn't see, and that is 2 times 2 times 3. These are factorizations with pairs of factors, but in this case I have 3 factors. Now let's look at this factorization and ask, can I factor 3 once again? The answer is no, because it's prime. The only factors it has is 1 and itself. But 4 can be factored. That is, it can be written in and of itself as a multiplication problem. 2 times 2. Now note, in this case, these are all prime numbers, and it's exactly the same as this. Now let's do the same thing over here. Ask, can I factor 2? That is, can I write it as a multiplication problem? The answer, except for the trivial case of using itself and 1, I can't. 2 is a prime number. But 6 I can. 6 is 2 times 3. And again, now that is the same as this. And of course, if I were to do this, I would eventually get down to this as well. If we factor, then any factor which can be factored even further, and we continue to do that until all of the factors are prime numbers, we call that version the prime factorization, a process so important in algebra that many textbooks will dedicate a whole chapter to that process alone. Let's state that formally. The prime factorization of a number is the number written as a product of prime factors, usually in exponent form. Now, let's give an example with this problem. Let's say your task is to prime factor 4,704. To find the factors of a number is the same thing as to find the divisors of a number. To find prime factors is to find prime number divisors. So usually we begin our process by concentrating on the lowest possible prime number, which is 2. And that's even, so we know that 2 will divide into it. So let's do that. And that gives us 2 factors of our original number. 2, a prime number, 2,352 as a non-prime because I can see it's even, which is the same thing as saying that 2 will still divide into the second factor, which is my quotient here. So dividing by 2 again, I get 1176, which is still divisible by 2. So dividing once again by 2, I get 588, which is still divisible by 2. So doing it once again, and once again, I get a quotient or factor which is not divisible by 2. So I go to the next lowest number in my prime list, which is 3, do a divisibility test. 1 and 4 is 5 and 7 is 12. 3 goes into that, so 3 goes into 147. So doing that, I get 49, which I can now simply see has a divisor of 7, and a second factor of 7, which tells me 7 goes in again. And I continue to divide progressively by prime numbers, ever increasing them, until I get a final quotient of 1. So what we're saying here is that 4,704 is 1 times 7 times 7, etc., down to this last 2. Or we can state our results this way. You can see that's fairly involved, and if this were much larger, this could stretch out quite a ways. So it becomes very convenient if we simply write this in exponent form. I have 5 2's being multiplied, so 5 becomes the exponent of 2. Only 1, 3, and 7 is a factor twice. So this form of writing this number we call the prime factorization of our number in exponent form. A very important process for those of you who will continue in your mathematics. Let's do one more problem smoothly to iron out any discomfort you might have from going too fast here. Let's try this problem. Now remember, our process is start dividing by the lowest possible prime, which is 2. Since the n digit is even, we know that 2 will divide it, so we begin that process. 2 goes in 321. That's not even, so 2 will not go in anymore. So we go to the next higher prime in our list, which is 3. Trying our divisibility test, 3, 2, and 1 is 6. 3 divides that. Doing that, we get 107. 1 and 7 is 8. 3 won't go into that, so we know we've used 3 as much as it can be used. Going to the next highest prime, it's 5. That's not 0 or 5, so 5 won't go in. Going to the next highest prime, 7. Well, 7 goes into 10 once with a remainder of 3, so that's 37, which 7 won't go in. So 7 won't go in. We don't even have to try 11 because the approximate square root of 107, well, 10 times 10 is 100, so that's close. And 11 times 11 is more than 107, so we need not go beyond that point, which tells me that this number must be prime. So my prime factorization of 642 is that times that times that. Prime factorization is used so much in future work that it also is contained in most math tables. It is used in algebra to reduce messy fractions, indeed to add and or subtract fractions with large denominators, and to find least common multiples, which is your next lesson. So this is a key lesson to many that are coming very soon. Really, it's that simple. However, a beginning student frequently, when they see a large number, they get somewhat uneasy thinking this is going to be a difficult task. Not really so if you remember all the tests that we've given you up to this point. So let's conclude this lesson with 2 more problems, but let's concentrate on some of the things we learned before this lesson. In particular, the divisibility test. They allow us to check the divisibility of this by at least the lower prime numbers, these 3 in particular. See, we can look at this number, and if the n digit is even, that means that 2 will divide into it. Since it is odd, 2 will not, so that rules that out without even trying to divide. Now, our divisibility test for 3 was to add the digits, so this is 3 plus 3 plus 3 is 9, which is divisible by 3, so that tells me to go ahead and divide by 3. And if I were to do it, I would get this as my second larger non-prime factor. Here lies an important realization. As soon as you have found one divisor, really you are through with this. So the number I'm dividing into is getting progressively smaller and smaller and smaller. So it is really pointless to think about whether this is big or small. That's irrelevant. The only relevant question is, can you find a divisor? Because if you can find one divisor, then the big dividend becomes automatically smaller. So again, using the divisibility test on 3, we can see that this is 7, and 1 is 9, which is divisible by 3. So is 711. So dividing it by 3, and with practice, there's nothing wrong with the calculator. In fact, it's encouraged. But dividing this by 3, we would get 237. And see, this is much, much, much smaller than what we started with. Again, before we leave this possible divisor, try it again. So 2 and 3 is 5, and 3 is 12, which is divisible by 3. So that tells us 3 works once again. So again, dividing by 3, we would get 79. And 7 and 9 is 16, so we're through with our 3's. We can see by our divisibility test for 5 that 5 will not divide into this, since this does not end in 5 or 0. So the next prime number we would try is 7, then 11, then 13. So the first realization is this. Don't worry about whether this number is large or small. In fact, prime factoring will generally in the future be of only strong value when the number is in fact quite large. But the point is to don't worry about the length or size of the number, simply find a divisor. And this number gets progressively smaller. See, now 79 is quite small, and we rather suspect that it might be a prime number. But the next realization we must keep at the back of our mind is the question, the answer to the question, how far must I go before I quit and say this in itself is prime if I don't know at the moment whether it is or is not? So recall at any point where you must pause, you want to ask yourself, what's the approximate square root of 79? And if you need to, find a calculator and actually punch in 79 square rooted. Comes out to be 8.8, which means, rounding down, that I need only try numbers less than 8, prime numbers at that. So this is not less than, nor is that, so that tells me 7 is the last I need try. But if I try 7, I can see visually it won't go into this. So if the numbers less than this will not divide into this, then that means numbers larger than won't either, hence this is a prime. So the prime factorization of 2133 is, in exponent form, 3 cubed, or 3 to the 3rd power, times 79. See, no matter how messy the number becomes, the principle stays the same, and it remains simple in concept. Let's do another, concentrating on the concept rather than the numbers. We want to divide this number repeatedly, not by just any old divisor, but by prime numbers. So that gives us a very short list. Now, a list that goes on forever, but there's a lot of numbers in between that we need never try. So we can tell by looking at it that 2 won't. We can also tell by looking at it that 5 won't. 3, we can try that test, divisibility test, mentally. Throw the 3 away. 2 and 8 is 10, and 9 is 19. 3 will not divide into 19, so we don't have to try that. In future uses of this prime factoring technique, it's not so important that one can do it by hand, although certainly we hope that you can, but that you can prime factor it by whatever means possible, including, of course, the calculator. So let's try this problem with a calculator. So the next prime number to try is 7. So we wish to see if 3, 2, 8, 9 is divisible by 7. And whenever we get a decimal after our division, that means that the divisor did not go in evenly, which is what we're looking for. So that rules that out. So now let's go to 11. So 3, 2, 8, 9 divided by 11 is 299. So 11 did divide in 299, isn't it? 11 might go again. So while we have the number here, let's remember what it is, then try dividing it by 11 once again. It didn't go in because of the decimals. So clear. Take the same number, 299. Now we're ready to try dividing by the next prime number. In this case, 13. And it went in evenly. And by now we've used this so much that we know it's one of our prime numbers. So 3289 prime factors to 11 times 13 times 23. So with the calculator and a list of prime numbers, this can become a fairly easy task even when this gets to be rather a longish numbers. So important is a list of prime numbers that most math textbooks and virtually all math handbooks will have in it somewhere a list of prime numbers. In the textbook that goes with these tapes, not only do we have a list of prime numbers on the inside jacket, but we also prime factor all the numbers up to, in this case, 100. Check most math books out, or certainly a good math handbook, and somewhere in it will be either a list of prime numbers and more often than not a long list of the prime factorizations of all the numbers up to some important point. It wouldn't be in the book if it wasn't to be used a considerable amount of times in your application problems. Therefore, let's conclude this lesson by concentrating on perhaps some efficient uses of the calculator. Here I'm using a rather expensive, sophisticated calculator, but what I'm going to say will work just as well on the simplest $4 or $5 calculator. First, you can check the lower prime numbers. We left out a 5 here, didn't we? By a visual inspection. We can see that 2 won't go into this because this isn't even. Adding the digits, 5 and 6 is 11, plus 9 is 20. 3 won't go into that. We can see visually that 5 won't go in. So now we need only start at 7 and work our way up. Now let me start working this a rather long way. And you watch me. In a few minutes, let's see if we can decide on a faster way of approaching this problem. Let's try this 7. We would take 569, divide by 7 equals, and we can see it does not go in evenly. So we'll move to 11, which means I must clear my calculator and re-enter that number, 569. Now try dividing by 11. So divide by 11. and it still won't go in evenly. So now we must go back to 13 and clear and re-enter that number. So if we get a long string of prime numbers which won't divide this, we have to repeatedly keep entering this over and over. So most calculators will have a memory, so that if you put your number into memory, you can clear your calculator, but it's still inside. By pushing the memory recall key, see, it's still there. I can use it like divide by 7 equal. When I see it won't go in, all I need to do is to push recall memory. My division has been erased, and this has been pulled out of memory and put back onto the calculator for me. So now I can simply put divide by 11 equals. Won't go in evenly, so push the recall key. I've erased and pulled this back with one punch. Now I'll go on to 13. So divide by 13 equal. That won't go in. So push the recall key. This is back on the calculator. I can go on to the next. Divide by 17 equals. That won't go in. So I can keep on using this recall key as long as I wish, and on most calculators, as long as you have the calculator on. Then on some calculators like this, in fact, we can indeed turn it off. Tomorrow, turn it back on, and it's still there and ready to go. It's features like that that usually cause a calculator to cost so much more, but be a little bit more useful. Now at this point, rather than trying numbers on and on and on and on forever, because indeed this might be prime, let's decide right now, how far should I go before I quit and say this is prime? I know that for sure. So we've recalled that number again from memory, and we're going to square root it. On this calculator, we square root it a little bit differently. On this one, I must push the square root key first, and then memory recall. On your calculator, that's probably reversed. You'll probably recall the number, then hit the square root key. And the square root is approximately 23. So that tells me I need try no number in this list greater than the square root of this, which in this case is only two of them, 19 and 23. So I recall my memory again. Divide by 19 equals. That won't go in. Recall once again. Divide by 23 equals. That won't go in. But that's the end of the line. So in this case, I know that this number is already a prime number. So do you see how very, very useful not only can a calculator be, but knowing how to use it. In this case, how to use that memory key is. So it's worth your while in this lesson, if you have a calculator, to play with it a bit and also learn how to use that memory key back and forth. That can save you an immense amount of time in future mathematical work. So let's conclude this lesson by letting you watch me do a problem very quickly on the calculator. First, even though I can see a 2 will go into it, I will enter the 564. Then I will divide by 2. You might say, why? You know it'll go in, because I know that 2 is one of my factors, and by dividing it by 2, I get the next smaller quotient, or the next factor, which I can also see divides by another 2. So recording it, dividing by 2, this gets smaller. I can still see I can divide by another 2, so divide by that 2 is smaller yet and still divisible by 2. So by dividing by another 2, it's smaller and still divisible by 2. So recording it, dividing by it, It's still smaller, but now I can see that 2 won't work anymore, but 3 will. So recording the 3, divide by 3 equals, and I can see the last one will be 3 times 3. So with very little practice, your calculator can be extremely efficient assistant. Now note, the calculator does not get you out of knowing the concepts of what prime numbers are, how to prime factor, how to write it in exponent form, which we will need for the future. The calculator simply allows you to organize your arithmetic itself, your dividing in this case. But what to do, when to do the division, and what to do with your answer, that is primarily what this lesson is about, that which we call the concepts of mathematics. Your next lesson will show you your first application of prime factorizations, but certainly it will not be your last nor the least important application. Again, we cannot stress enough that if you're going on into collegiate math, this concept is very important and will be used over and over in just about every math course which follows this one. So do a good job here. This is your math host, Bob Fennell. We'll see you at the next lesson. Good luck.